Welcome to Tech with Koushik. This is set 3 of our AI-300 Microsoft Certified Machine Learning Operations Engineer Associate Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link is in the description. Let us begin set 3. The next item is question number 87. This question focuses on our AG retrieval tuning. Scenario. A policy assistant, our AG pipeline, frequently returns retrieve passages that are either incomplete or poorly scoped to the source section. The generation settings are otherwise unchanged. Which retrieval ingestion setting should the team tune first to improve the boundaries and contextual completeness of retrieve passages? Available choices. Option A, generation temperature. Option B, chunk size and overlap. Option C, maximum generation token count. Option D, embedding strategy. The required response is option B, chunk size and overlap. This is correct because chunk size and overlap determine how source material is divided for indexing and retrieval. Poor boundaries can split related content or return fragments that omit needed context. So these settings directly affect the completeness and scope of retrieve passages. The alternatives can be eliminated because A, temperature changes generation variability after retrieval. It does not repair passage segmentation. C, the generation token limit controls output length, not which source passages are retrieved. D, response timeout is an operational setting and does not improve retrieval relevance or completeness. Remember this distinction for the exam. When the problem is how source content is segmented or how much neighboring context a retrieve passage contains, tune chunk size and overlap before generation parameters. Review question number 88. Carefully. Let us first review the situation. A regulated company wants to fine-tune a generative model, but is prohibited from using real customer conversations as training examples. The new examples must resemble the prompts and responses expected for the target task. What should the team do? Choose from the following options. Option A is use a simulator to generate synthetic prompt response interactions for the target task. Option B is treat runtime telemetry traces as labeled fine-tuning examples. Option C is capture live A/B test traffic despite the compliance restriction. Option D is export evaluation logs unchanged and use them as training data. The correct answer is option A. Use a simulator to generate synthetic prompt response interactions for the target task. The key reason is a simulator can create task-aligned synthetic interactions without exposing restricted production conversations, giving the fine-tuning workflow prompt response examples that resemble the intended use case. The other choices do not satisfy the requirement because B, telemetry traces are operational data and are not automatically valid labeled fine-tuning examples. C, capturing live traffic contradicts the compliance restriction. D, evaluation logs are not necessarily formatted or labeled as the required fine-tuning interactions. A useful examination rule is this. Synthetic fine-tuning data should reproduce the target task structure while respecting data governance constraints. Operational logs are not automatically training data. Now consider question number 89. Treat this as a medium question. Review the situation. A team needs to improve AG application's retrieval quality. It wants to diagnose current retrieval behavior before changing ingestion settings and rebuilding the index. Arrange the 4 actions in the appropriate sequence. 2 items will not be used. The available items are: Entry 1, change the model temperature. Entry 2, re-index the documents. Entry 3, collect retrieval logs for representative queries. Entry 4, regenerate the prompt template. Entry 5, run our AG evaluators against the collected behavior. Entry 6, adjust the chunking strategy based on the evaluation findings. The completed sequences. The first item is collect retrieval logs for representative queries. The second item is run our AG evaluators against the collected behavior. The third item is adjust the chunking strategy based on the evaluation findings. The fourth item is re-index the documents. The requirement is satisfied because the team first gathers evidence about current retrieval behavior and evaluates it. Only then should it choose an ingestion/retrieval change. Because chunking affects indexed document representation, The documents must be re-indexed after the chunking configuration changes. Keep this examination point in mind. Use an evidence-driven RAG loop. Observe, evaluate, tune the retrieval/ingestion configuration, then rebuild affected index artifacts. Let us focus on question number 90. This scenario establishes the key requirement. An Azure Machine Learning workspace must register one tabular metadata asset that can reference image file paths located in two Azure Blob Storage accounts. The asset definition needs multiple paths, and each path directly addresses an Azure Blob container. Complete the data asset configuration. Review statement 1, data asset type, the blank. The options for this statement are 1. MLTable, URI_file, or URI_folder. Review statement 2, URL scheme for direct Azure Blob Storage paths, the blank. The options for this statement are 2. WASPs, ABS, or AzureML. The answer to the first statement is MLTable. MLTable supports a definition containing multiple source paths and a materialization blueprint. The answer to the second statement is WASPs. WASPs addresses Azure Blob Storage containers directly. Exam tip. Match the URI scheme to the storage service. WASP for blob storage paths, ABS for ADLS generation 2 hierarchical paths, and AzureML for Azure Machine Learning Asset/Datastore references. Let us work through question number 91. Consider the following scenario. A notebook experiment in Azure Machine Learning records a numerical validation value at several training steps. The values must appear as MLflow metrics so that the run can be compared in the workspace. Which MLflow function should the notebook call for each numerical metric value? Now examine the possible answers. Choice A, mlflow.log_artifact. Choice B, mlflow.log_image. Choice C, mlflow.log_metric. Choice D, mlflow.log_batch. The best answer is option C, mlflow.log_metric. The reasoning is as follows. mlflow.log_metric records a numeric metric value for an MLflow run and can be called repeatedly, optionally with steps, to record a numerical series over training iterations. Now consider why the remaining options are unsuitable. A. mlflow.log_artifact records files rather than numerical metric values. B. mlflow.log_image records images. D. mlflow.log_batch is not the appropriate top-level function for logging the individual numerical metric values described. Use MLflow metric logging for numeric run measurements, parameter logging for configuration values, and artifact logging for files produced by the run. Question number 92 highlights an important distinction. This question moves us into our AG evaluation. Focus on the following situation. A Microsoft Foundry RAG application generates fluent answers, but some claims are unsupported by the retrieved documents. A proposed change is being evaluated. The team needs a supported, measurable method to determine whether grounding quality improved. One proposal is to judge the change only by reading free-form user comments collected after release. For each statement, select yes if the statement is true. Otherwise, select no. The first statement is, reviewing only post-deployment user comments is sufficient to measure whether the change improved grounded RAG answer quality. The answer to statement 1 is no. Controlled evaluation with grounding-related metrics is required to measure the change consistently. The key takeaway is user feedback is useful evidence, but release quality RAG validation needs repeatable evaluation data and explicit metrics for properties such as groundedness and relevance. Proceed to question number 93. A data platform team has an existing Azure Blob Storage container that holds many training and validation folders. Multiple Azure Machine Learning jobs must access different paths in that storage account. The team wants to manage the storage connections centrally without registering each folder as a specific reusable dataset. Which Azure Machine Learning resource should the team create? Review the options. Choice A, an Azure Machine Learning data store. Choice B, a URI_folder data asset for the entire storage account. Choice C, an Azure Machine Learning environment. Choice D, an Azure Machine Learning model asset. The appropriate choice is option A, an Azure Machine Learning data store. Here is the technical justification. A data store provides a centrally managed connection abstraction for supported storage services. Jobs and assets can reference paths through the data store without requiring every storage folder to be registered as its own data asset. The incorrect choices fail for the following reasons. B. A data asset represents managed data used by ML workloads. It is not the general storage connection abstraction requested here. C. An environment defines runtime dependencies and images. D. A model asset versions train model artifacts rather than storage connectivity. Remember this distinction for the exam. Data store equals connection to storage. Data asset equals managed reference to specific data used by jobs. Question number 94. Requires careful analysis. Identify the decisive requirement in this scenario. An Azure Machine Learning Compute cluster must read training files from an Azure Blob Storage container. Security policy prohibits storing storage account keys, SAS tokens, or service principal secrets in the workspace data store. Complete the credentialless data access configuration. The first statement reads, configure the data store to use the blank. Select from 1. Identity-based authentication, account key authentication, or SAS token authentication. The second statement reads, grant the compute identity at least to the blank role on the storage account for read-only blob access. Select from 2. Storage blob data reader, or Azure ML data scientist. For statement 1, select identity-based authentication. Identity-based access uses Microsoft Intra or managed identity rather than a stored key, SAS token, or service principal secret. For statement 2, select storage blob data reader. This role grants the data plane permissions needed to read blob data without granting unnecessary write access. A useful examination rule is this. Credentialless AML data access requires both identity-based authentication and storage data plane, or BAC, for the identity that reads the data. Question number 95. We are moving to AML identity and our BAC. Consider this scenario. Contoso uses one Azure Machine Learning workspace. Data scientists must create and update jobs, models, environments, and other workspace assets, but they must not create or delete compute resources or modify the workspace itself. A separate operations group must create, manage, and delete Azure Machine Learning compute resources without receiving full workspace ownership. Which 2 built-in role assignments best implement the required separation of duties? Choose 2. More than one answer may be correct. The options are: Option A, assign Azure ML data scientist to the data scientists. Option B, assign Azure ML compute operator to the operations group. Option C, assign owner to the data scientists. Option D, assign contributor to both groups. Option E, assign reader to the operations group. The choices that satisfy the requirement are Option A, assign Azure ML data scientist to the data scientists, and Option B, assign Azure ML compute operator to the operations group. Azure ML data scientist supports normal workspace data science actions while excluding compute creation/deletion and workspace modification. Azure ML compute operator is designed for creating, managing, deleting, and accessing workspace compute resources. The remaining options are incorrect because C, owner grants full workspace control and role assignment capabilities, violating least privilege. D, contributor grants broader workspace and compute management permissions than the stated separation requires. E, reader is read-only and cannot manage compute resources. Keep this examination point in mind. Combine Azure ML data scientist and Azure ML compute operator when experimentation and compute administration must be separated. Now consider question number 96. Background. Fabricam Research trains models in Azure Machine Learning by using a managed compute cluster. Training data is stored in a private Azure Blob Storage account. Current environment. Data scientists submit training jobs to the cluster. They do not have direct permissions to the storage account. The existing data store must be reconfigured because the organization is eliminating stored access keys and SAS tokens. Business requirements. Training jobs must continue to read the private training data while keeping individual data scientists from receiving direct storage access. Technical requirements. Authentication must use an Azure managed identity. No storage credentials may be stored in the data store. Which 2 actions should the platform team perform? You need to identify 2 correct options. Choice A, enable a managed identity on the Azure Machine Learning Compute cluster and grant its storage blob data reader on the storage account. Choice B, Configure the Azure Machine Learning Data Store to use identity-based authentication. Choice C. Store a long-lived SAS token in the data store so every training job can reuse it. Choice D. Grant every data scientist storage blob data reader on the storage account. Choice E. Store the storage account key in a GitHub repository secret and inject it into each job. The correct answers are Option A. Enable a managed identity on the Azure Machine Learning Compute Cluster and grant it storage blob data reader on the storage account, and Option B. Configure the Azure Machine Learning Data Store to use identity-based authentication. This is correct because identity-based data store access avoids stored storage secrets. The compute cluster managed identity can authenticate during training jobs, and storage blob data reader grants the minimum blob data plane permission required to read the private training data. C. SAS token is a stored credential and violates the requirement. D. Direct user storage permissions are unnecessary because the compute identity should access the data. E. Storing and injecting an account key reintroduces a long-lived secret. Exam tip. For private training data, use an identity-based data store plus or BAC on the storage resource for the job or compute identity. The next key item is question number 97. Next, we enter the topic of AML components. The central scenario is as follows. A machine learning team is converting a collection of ad hoc scripts into reusable Azure machine learning assets and pipelines. Match each operational requirement to the most appropriate Azure machine learning concept. Each concept is used once. Review the items in the left column. Left item 1. Package a reusable executable pipeline step with defined inputs, outputs, code, command, and runtime reference. Left item 2. Define the Python packages and base image required by that executable step. Left item 3. Create a reusable managed reference to training data. Left item 4. Orchestrate multiple steps so outputs from one step can be consumed by later steps. Choose matches from the following right side entries. Choice A on the right, command component. Choice B on the right, environment. Choice C on the right, data asset. Choice D on the right, pipeline job. The correct pairings are. The correct match for package a reusable executable pipeline step with defined inputs, outputs, code, command, and runtime reference is command component. The correct match for define the Python packages and base image required by that executable step is environment. The correct match for create a reusable managed reference to training data is data asset. The correct match for orchestrate multiple steps so outputs from one step can be consumed by later steps is pipeline job. The key reason is components package reusable executable logic with declared interfaces. Environments define runtime dependencies. Data assets manage reusable data references, and pipeline jobs compose steps and data dependencies into repeatable workflows. Component equals reusable step. Environment equals runtime. Data asset equals data reference. Pipeline equals orchestration. Question number 98. Review the situation. A team wants a reusable Azure Machine Learning command component for data preparation. Pipelines must reference a registered component version, and a later implementation change must not silently alter pipelines that use the original version. Select the 4 required actions and arrange them in a logical lifecycle order. One item will not be used. Build the sequence from the following entries. The first available item is reference the registered component version from the pipeline. The second available item is when the implementation changes, register the changed component as a new version. The third available item is define the component interface, code, command, and environment. The fourth available item is install dependencies independently inside every downstream training script instead of using the component. The fifth available item is register the initial component version in the Azure Machine Learning workspace. Here is the proper order. First, define the component interface, code, command, and environment. Second, register the initial component version in the Azure Machine Learning workspace. Third, reference the registered component version from the pipeline. Fourth, when the implementation changes, register the changed component as a new version. The requirement is satisfied because a component must first be defined and registered before a pipeline can reference its version. Version registration preserves reproducibility. Later implementation changes should create a new component version rather than silently changing the version already used by pipelines. The key takeaway is register reusable components by version so pipeline dependencies remain reproducible when implementation changes. The next item is question number 99. The focus now shifts to GitHub AML integration. Background. AdventureWorks stores Azure Machine Learning infrastructure definitions in GitHub and deploys them through GitHub Actions. Current environment. The workflow uses Azure CLI and Bicep to provision resources in a dedicated resource group. The organization currently stores a client secret for Azure authentication in GitHub. Business requirements. The security team wants to eliminate long-lived Azure credentials from GitHub while retaining unattended deployment from approved repository workflows. Technical requirements. Authentication must use OpenID Connect Federation. The Azure identity must have only the Azure permissions required for the deployment scope. Which 3 actions should the team perform? Select 3 answers that satisfy the requirement. The options are: Option A, configure a federated identity credential on a Microsoft Intra application or user-assigned managed identity that trusts the GitHub repository workflow. Option B, assign the federated Azure identity an appropriate Azure RBAC role at the required deployment scope. Option C, configure the workflow to use the Azure login action with OIDC and request an ID token. Option D, store a replacement client secret in an encrypted GitHub Actions secret. Option E, use a GitHub personal access token as the Azure credential. Select Option A. Configure a federated identity credential on a Microsoft Intra application or user-assigned managed identity that trusts the GitHub repository workflow. Option B. Assign the federated Azure identity an appropriate Azure RBAC role at the required deployment scope. And Option C. Configure the workflow to use the Azure login action with OIDC and request an ID token. The reasoning is as follows. OIDC authentication requires a federated identity credential that trusts GitHub-issued tokens, Azure RBAC authorization for the identity, and a workflow that obtains an ID token and signs in to Azure without a client secret. The alternatives can be eliminated because D. Replacing one stored client secret with another does not eliminate long-lived credentials. E. A GitHub personal access token authenticates to GitHub resources. It is not the Azure federated identity required by this design. Remember this distinction for the exam. GitHub OIDC to Azure needs trust configuration, Azure RBAC, and an ID token-enabled Azure login workflow, no long-lived client secret. We will now analyze question number 100. Review the scenario carefully. A data science team has an ML table containing labeled binary classification training data. The team wants Azure Machine Learning to automatically explore supported algorithms and configurations. The business requirement is to maximize classification accuracy. Complete the Azure Machine Learning SDK v2 AutoML configuration. For the first statement, configure the job by using the blank. The available choices are 1. AutoML.classification, AutoML.regression, or a batch endpoint. For the second statement, set the primary metric to the blank. The available choices are 2. Accuracy, normalized __ scored _ error, or a 2 _ score. Statement 1 should be completed with AutoML.classification. SDK v2 uses the task-specific AutoML classification factory for tabular classification workloads. Statement 2 should be completed with accuracy. The business requirement explicitly asks AutoML to maximize classification accuracy. A useful examination rule is this. AutoML job type follows the prediction task. Primary _ metric defines how candidate AutoML trials are ranked. Proceed to question number 101. Background. A computer vision team trains a PyTorch model in Azure Machine Learning. The training script already uses PyTorch distributed data parallel. Current environment. The target Azure Machine Learning GPU compute cluster has 4 nodes available. Each node has 8 GPUs. Business requirements. One training job must use all 4 nodes and all 8 GPUs on each node. Technical requirements. Use Azure Machine Learning SDK v2 distributed job configuration. Do not replace the training workload with hyperparameter tuning or automated ML. Which 2 job settings should the team configure? Select exactly 2 answers. Available choices. Choice A. Set instance _count to 4. Choice B. Configure PyTorch distribution with process _count _ per _ instance set to 8. Choice C. Set instance underscore count to 1 and rely on the script to allocate the other 3 nodes automatically. Choice D. Convert the command job to a sweep job. Choice E. Deploy the model to a batch endpoint before starting training. The required selections are Option A. Set instance underscore count to 4 and Option B. Configure PyTorch distribution with process underscore count underscore per underscore instance set to 8. Here is the technical justification. Instance underscore count controls the number of nodes used by the command job. For distributed PyTorch, process underscore count underscore per underscore instance controls the number of worker processes launched on each node and typically matches the number of GPUs per node. The other choices do not satisfy the requirement because C. One instance requests only one node. The training script does not automatically allocate additional Azure ML nodes. D. A sweep job varies hyperparameters and does not configure distributed execution of one trial. E. A batch endpoint is an inference mechanism, not a distributed training prerequisite. Keep this examination point in mind. For distributed PyTorch in AML, scale across nodes with instance underscore count and across GPUs per node with process underscore count underscore per underscore instance. Proceed to question number 102. This one is marked hard. Eliminate the options systematically. Scenario. A team is operationalizing a repeatable Azure machine learning training workflow. Data preparation, model training, and model evaluation should be reusable steps. The output of each required step must flow to the next step, and the resulting candidate should be registered only after the pipeline has produced and evaluated it. Select the 4 required actions and arrange them in a logical implementation order. 2 items will not be used. Review the items to be ordered. Item 1. Submit the composed pipeline job to Azure Machine Learning. Item 2. Register the evaluated candidate model when it meets the required acceptance criteria. Item 3. Define or register reusable components for data preparation, training, and evaluation. Item 4. Deploy an online endpoint before the training pipeline is submitted. Item 5. Compose the pipeline by binding component outputs to the required downstream inputs. Item 6. Manually copy intermediate files between pipeline steps after each job finishes. Arrange the items in this order. In position 1, define or register reusable components for data preparation, training, and evaluation. In position 2, compose the pipeline by binding component outputs to the required downstream inputs. In position 3, submit the composed pipeline job to Azure Machine Learning. In position 4, register the evaluated candidate model when it meets the required acceptance criteria. Reusable components establish the steps. The pipeline then binds upstream outputs to downstream inputs before submission. After execution produces and evaluates a candidate, the accepted model can be registered as a governed model asset. Exam tip. Build pipelines from reusable components, wire outputs to inputs, submit the graph, and promote only evaluated model artifacts. Let us focus on question number 103. Focus on the following situation. A platform team is organizing several generative AI applications in Microsoft Foundry. The organization wants shared top-level governance while allowing each application team to work in its own isolated development boundary. Match each requirement to the most appropriate Microsoft Foundry scope. A scope may be used more than once. Begin with the following left-side entries. Left side, entry 1. Provide the parent Azure resource under which multiple application projects can be created. Left side, entry 2. Organize one application's agents, evaluations, files, and related development work. Left side, entry 3. Apply project-specific access for developers who should not administer the parent resource. Left side, entry 4. Manage the common Foundry account that owns the projects. The second set contains right side, entry A, Foundry resource. Right side, entry B, Foundry project. Here are the completed matches. Pair provide the parent Azure resource under which multiple application projects can be created. And Foundry resource. Pair organize one application's agents, evaluations, files, and related development work. And Foundry project. Pair apply project-specific access for developers who should not administer the parent resource. And Foundry project. Pair manage the common Foundry account that owns the projects. And Foundry resource. This is correct because a Foundry project is created on a parent Foundry resource. Projects organize application work such as agents, evaluations, and files, while the parent resource provides the account-level Azure resource and common management boundary. Foundry resource is the parent Azure account. Projects are the application-level work and access boundaries created under it. The next item is question number 104. We are now working with Foundry environments. A company is creating a new Microsoft Foundry environment for an application team. No suitable Foundry resource exists yet. The application team must receive project-level development access without being given administrative control over the parent Foundry resource. Select the 4 required actions and arrange them in a logical provisioning order. One item will not be used. The sequence must use these items. Item 1. Assign the application team the Foundry user role at the project scope. Item 2. Create the Foundry project under the Foundry resource. Item 3. Create the Foundry resource with project management enabled. Item 4. Create or select the Azure resource group for the Foundry resource. Item 5. Grant every developer owner at the subscription scope. The correct sequence is as follows. In position 1, create or select the Azure resource group for the Foundry resource. In position 2, create the Foundry resource with project management enabled. In position 3, create the Foundry project under the Foundry resource. In position 4, assign the application team the Foundry user role at the project scope. The key reason is the Foundry resource requires an Azure resource group and is the parent of the project. The project must exist before the application team can receive project-scoped Foundry user access. Subscription owner for every developer would violate least privilege. The key takeaway is provision the Foundry parent before the project, then grant developers access at the narrowest project scope that satisfies their work. Now consider question number 105. Background. Contoso builds AR-AG agent in a Microsoft Foundry project. The agent queries an existing Azure AI search index. Current environment. The search service is configured for Microsoft Intra ID role-based access. The project does not store a search API key. Business requirements. The agent must query the search index without storing credentials. Technical requirements. Use the Foundry project's system-assigned managed identity and grant only the permissions required for read-only query access to the index. Which 2 actions should the platform team perform? Choose the best 2 responses. Review the options. Option A. Enable a system-assigned managed identity for the Foundry project. Option B. Assign search index data reader on the Azure AI search service to the project's managed identity. Option C. Assign search index data contributor because every query requires write permission. Option D. Store an Azure AI search admin key in the project connection. Option E. Assign owner on the Azure AI search service to every application developer. The choices that satisfy the requirement are Option A. Enable a system-assigned managed identity for the Foundry project, and Option B. Assign search index data reader on the Azure AI search service to the project's managed identity. The requirement is satisfied because the project managed identity provides keyless authentication. Search index data reader supplies read-only data plane access to query the search index, satisfying least privilege without storing an Azure AI search key. Now consider why the remaining options are unsuitable. C. Search index data contributor permits index document rights and is unnecessary for read-only querying. D. An admin key violates the no stored credential requirement. E. Giving human developers owner is unnecessary and far broader than runtime query access. Remember this distinction for the exam. For read-only Foundry to AI search access, combine the project managed identity with search index data reader on the search service. Let us examine question number 106. The difficulty level here is medium. Begin by examining the scenario. A Microsoft Foundry project uses a customer-owned Azure storage account for project data. The Foundry runtime must create, read, and update blobs in that account. Security policy prohibits storage account keys and SAS tokens. Complete the keyless access configuration. Statement 1. Use the Foundry project's the blank to authenticate to Azure storage. Choose between 1. Managed identity, shared access signature, or account key. Statement 2. Assign that identity to the blank role on the storage account. Choose between 2. Storage blob data contributor, storage blob data reader, or reader. The correct value for statement 1 is managed identity. Managed Identity supports Microsoft Intra-Authentication without account keys or SAS tokens. The correct value for statement 2 is storage blob data contributor. The runtime needs blob read and write operations, which require data plane contributor permissions rather than read-only access. A useful examination rule is this. Choose the storage data plane role from the required operations. Reader for reads only. Contributor when the runtime must create or update blobs. Let us examine question number 107. Begin by examining the scenario. A company uses one Microsoft Foundry resource with several projects. Platform administrators must create and manage projects at the parent resource. Developers for Project Claims Agent must build and test AI applications only in that project and should not receive parent resource administration permissions. Which two role assignments best implement least privilege? Choose 2. Identify all valid responses. Compare the following options. Option A is assign Foundry account owner to platform administrators at the Foundry resource scope. Option B is assign Foundry user to Claims Agent developers at the Claims Agent project scope. Option C is assign owner to all developers at the subscription scope. Option D is share the Foundry resource API key with both groups instead of using RBAC. Option E is assign Foundry account owner to Claims Agent developers at the parent resource scope. Select Option A. Assign Foundry account owner to platform administrators at the Foundry resource scope, and Option B. Assign Foundry user to Claims Agent developers at the Claims Agent project scope. The reasoning is as follows. Foundry account owner gives administrators the parent resource and project management authority they require. Foundry user gives developers project development permissions without granting the same parent resource management authority. The incorrect choices fail for the following reasons. C. Subscription owner is far broader than required. D. Shared keys bypass user-specific RBAC and weaken separation of duties. E. Giving developers the account owner role at the parent resource violates the stated least privilege boundary. Keep this examination point in mind. Use administrative Foundry roles at the resource scope and development roles at project scope when teams have different control plane responsibilities. We will now analyze question number 108. The focus now shifts to Foundry private networking. Review the scenario carefully. A Microsoft Foundry resource must be reachable by application clients only through a corporate virtual network. Public inbound access to the Foundry endpoint is prohibited. The requirement does not by itself require isolated outbound traffic from Foundry to dependencies. Which configuration directly satisfies the inbound access requirement? Review each available choice. Choice A. Create a private endpoint for the Foundry resource and disable public network access. Choice B. Keep public network access enabled and rotate the API key every day. Choice C. Enable global provision throughput for every model deployment. Choice D. Create a public IP allow list, but leave unrestricted public endpoint access enabled. In this case, select Option A. Create a private endpoint for the Foundry resource and disable public network access. Here is the technical justification. A private endpoint gives clients a private network path to the Foundry endpoint. Disabling public network access prevents callers from reaching the resource through its public endpoint, directly satisfying the inbound isolation requirement. The remaining options are incorrect because B. Key rotation does not make the endpoint private. C. Model throughput type does not control inbound network reachability. D. Leaving unrestricted public endpoint access enabled violates the requirement. Exam tip. Private endpoint addresses inbound private connectivity. Outbound isolation is a separate networking decision. Question number 109. Background. A regulated company deploys an agent application through Microsoft Foundry. The agent accesses private Azure services, and the company manages its own network address space, routing, firewall, and peering. Current environment. The Foundry endpoint must not be exposed publicly. The application also requires isolated outbound connectivity from the agent runtime through the company's network. Business requirements. Both inbound and outbound paths must remain private. Technical requirements. Use a customer-managed virtual network rather than public egress. Which two configurations should the platform team implement? Select exactly 2 answers. Choice A. Configure a private endpoint for inbound access to the Foundry endpoint. Choice B. Configure virtual network injection by using the customer-managed virtual network and delegated subnet. Choice C. Keep public egress enabled because a private endpoint automatically isolates outbound traffic. Choice D. Enable public network access so the runtime can reach private dependencies. Choice C. Replace Microsoft Entra authentication with a shared API key. The required selections are Option A. Configure a private endpoint for inbound access to the Foundry endpoint, and Option B. Configure virtual network injection by using the customer-managed virtual network and delegated subnet. The private endpoint provides private inbound access. Customer-managed virtual network injection isolates agent egress through the organization's network, allowing its routing, peering, and firewall controls to govern outbound connectivity. C. A private endpoint alone secures inbound access and does not automatically isolate public egress. D. Public network access contradicts the private inbound requirement. E. Authentication method does not replace network isolation. For fully isolated Foundry agent networking, treat inbound private endpoint and outbound virtual network injection as separate controls. Review question number 110. Carefully. This is a hard-level item, so avoid choosing too quickly. Let us first review the situation. A platform team deploys a Microsoft Foundry resource and project with Bicep at resource group scope. The project is declared under the Foundry resource and has its own system-assigned managed identity. For each statement, select yes if the statement is true. Otherwise, select no. Statement 1. A resource group-scoped Bicep deployment can provision the Foundry resource and its project in the target resource group. Statement 2. The project's system-assigned managed identity is a separate resource identity from the parent Foundry resource's system-assigned managed identity. Statement 3. Giving the parent Foundry resource a system-assigned managed identity automatically gives the project that same identity without declaring an identity for the project. For the first statement, choose yes. Foundry resources and project child resources can be deployed through resource group-scoped infrastructure as code. For the second statement, choose yes. Each resource with system-assigned identity receives its own identity. For the third statement, choose no. System-assigned identities are resource-specific and are not automatically inherited by child projects. The key takeaway is do not confuse Azure resource hierarchy with managed identity inheritance. System-assigned identities belong to individual resources. The next item is question number 111. Consider this scenario. An operations team will use Azure CLI to provision a new Microsoft Foundry resource and its first project in a new resource group. The resource and project do not yet exist. Select the 4 required actions and arrange them in a logical provisioning order. One item will not be used. Review the items to be ordered. Entry 1. Create the Foundry project under the existing Foundry resource. Entry 2. Create the Azure resource group. Entry 3. Create the Foundry resource with project management enabled. Entry 4. Authenticate to Azure and select the intended subscription. Entry 5. Create a model deployment before the parent Foundry resource exists. The correct sequence is as follows. First, authenticate to Azure and select the intended subscription. Second, create the Azure resource group. Third, create the Foundry resource with project management enabled. Fourth, create the Foundry project under the existing Foundry resource. This is correct because Azure CLI must operate in the intended subscription before resources are created. The resource group contains the Foundry resource, and the project is created under that existing parent resource. A model deployment cannot precede the parent resource. Remember this distinction for the exam. For Foundry CLI provisioning, establish Azure context and parent resources before creating project-level resources. Let us work through question number 112. We are moving to Foundation Model Deploy. Consider the following scenario. An enterprise will host 3 different generative AI workloads in Microsoft Foundry. The workloads have different traffic and model hosting requirements. Match each deployment approach to the workload it best satisfies. Each approach is used once. The first set contains Item 1 on the left, bursty requests to a Foundry model sold by Azure with minimal capacity planning and pay-per-token billing. Item 2 on the left, predictable sustained requests to a supported Foundry model sold by Azure that require reserved throughput and consistent latency. Item 3 on the left, an open-source community model that must run on dedicated GPU capacity managed by Foundry. The right side choices are right option A, standard pay-per-token deployment. Right option B, provisioned throughput deployment. Right option C, managed compute deployment. Use the following matching result. Match bursty requests to a Foundry model sold by Azure with minimal capacity planning and paper token billing. With standard paper token deployment. Match predictable sustained requests to a supported Foundry model sold by Azure that require reserved throughput and consistent latency. With provisioned throughput deployment. Match an open-source community model that must run on dedicated GPU capacity managed by Foundry. With managed compute deployment. The key reason is standard paper token minimizes capacity planning for variable traffic. Provisioned throughput reserves model capacity for predictable, sustained workloads. Managed compute hosts open source and community models on Foundry-managed dedicated GPU capacity. A useful examination rule is this. Standard equals consumption. Provisioned equals reserved model throughput. Managed compute equals dedicated GPUs for open source/community models. Let us work through question number 113. Let us first review the situation. A company chooses an open source model from the Microsoft Foundry model catalog. The organization needs dedicated GPU capacity, Foundry-managed runtime patching, scaling controls, private networking support, and the same Foundry project endpoint and observability surface used by its other model deployments. Which deployment option should the company use? Compare the following options. Choice A, managed compute. Choice B, global standard. Choice C, global batch. Choice D, developer deployment. The appropriate choice is option A, managed compute. The requirement is satisfied because managed compute is designed for open source and community models that need dedicated GPU capacity, while Foundry manages runtime, infrastructure patching, scaling integration, networking, endpoint access, and observability. The alternatives can be eliminated because B, global standard is paper token hosted capacity for eligible Foundry models rather than dedicated GPU hosting for this open source model. C, global batch is asynchronous batch inference. D, developer deployment is intended for temporary fine-tuned model evaluation rather than dedicated production GPU hosting. Keep this examination point in mind. Choose managed compute when the model requires dedicated Foundry-managed accelerator capacity rather than serverless token-based hosting. Question number 114. This question moves us into provisioned throughput. Background. A customer support application uses a Foundry model sold by Azure. Traffic is high and sustained throughout the business day. Current environment. The application currently uses paper token capacity and experiences unacceptable latency variation at peak volume. Business requirements. The new deployment must provide predictable dedicated model throughput and more consistent latency. Technical requirements. The team will use a provisioned deployment in a selected Azure region. Before deployment, it must verify that the selected model can be provisioned there and that sufficient capacity entitlement is available. Which two checks should the team perform before creating the provisioned deployment? Select two answers that satisfy the requirement. Option A, verify that the model supports a provisioned deployment type in the target region and note its minimum PTU requirement. Option B, verify that the subscription has sufficient provisioned throughput unit quota for the target region and deployment type. Option C, verify that Azure VM virtual CPU quota is high enough because PTU quota is the same as VM quota. Option D, confirm that a global standard deployment already exists because provisioned deployments cannot be created independently. Option E, confirm that the workload is asynchronous because provisioned throughput supports only batch inference. The correct answers are option A. Verify that the model supports a provisioned deployment type in the target region and note its minimum PTU requirement, and option B. Verify that the subscription has sufficient provisioned throughput unit quota for the target region and deployment type. The reasoning is as follows. Provisioned deployment availability and minimum PTUs vary by model. PTU quota is also scoped by subscription, region, and deployment type, so the team must confirm both model support/minimum size and available PTU quota before deployment. The other choices do not satisfy the requirement because C, PTU quota is separate from Azure VM quota. D, a provisioned deployment does not require an existing global standard deployment. E, provisioned throughput supports real-time workloads and is not limited to batch inference. Exam tip. Before creating PTU capacity, validate model/region support, minimum PTUs, and quota for the exact region and provisioned deployment type. Review question number 115. Carefully. Consider the following scenario. A platform team is selecting deployment types for 2 Foundry models sold by Azure. Drag each deployment type to the workload it best satisfies. The items to be placed are: Source 1, Global Standard. Source 2, Global Provisioned. The target positions are: Target A, variable or bursty global traffic where paper token billing and minimal capacity planning are preferred. Target B, predictable sustained global traffic that requires reserved capacity and lower latency variance. The first mapping connects global standard to variable or bursty global traffic, where paper token billing and minimal capacity planning are preferred. The second mapping connects global provision to predictable sustained global traffic that requires reserved capacity and lower latency variance. Here is the technical justification. Global standard uses paper token capacity and suits variable workloads. Global provision reserves model processing capacity through PTUs and is designed for predictable high-volume workloads requiring more consistent throughput and latency. Use standard for elastic consumption and provisioned for sustained workloads that justify reserved throughput capacity. Let us examine question number 116. Next, we enter the topic of production model strategy. Begin by examining the scenario. A production application currently calls model version v1 through a stable application configuration. A new foundation model version v2 must be validated before production adoption. The previous deployment should remain available until the team is confident that v2 is stable. Select the 4 required actions and arrange them in the safest promotion order. One item will not be used. Build the sequence from the following entries. The first available item is remove the v1 deployment before evaluating v2. The second available item is create a separate deployment for model version v2. The third available item is evaluate v2 with representative quality, safety, latency, and cost tests. The fourth available item is update the production application or routing configuration to use the validated v2 deployment. The fifth available item is retain the v1 deployment as a rollback target until the v2 observation period is complete. Here is the proper order. The first item is create a separate deployment for model version v2. The second item is evaluate v2 with representative quality, safety, latency, and cost tests. The third item is update the production application or routing configuration to use the validated v2 deployment. The fourth item is retain the v1 deployment as a rollback target until the v2 observation period is complete. A separate candidate deployment lets the team validate the new model version without destroying the known good version. Production should move only after evaluation, and the previous deployment should remain available through the observation window for rapid rollback. The key takeaway is safe foundation model promotion separates candidate deployment, validation, production switch, and rollback target retirement. Question number 117 highlights an important distinction. This scenario establishes the key requirement. A Microsoft Foundry application has a sudden increase in inference cost after a prompt template change. Request volume is approximately unchanged. Operations wants to determine whether longer prompts or longer generated responses are driving the increase. Which 2 usage metrics should the team compare before and after the change? Choose 2. Select all answers that apply. Focus on the distinction between these options. Now examine choice A, input token consumption. Now examine choice B, output token consumption. Now examine choice C, number of Git commits. Now examine choice D, embedding vector dimensions in an unrelated index. Now examine choice E, number of registered evaluation datasets. Select option A, input token consumption, and option B, output token consumption. This is correct because input tokens quantify prompt/context size and output tokens quantify generated response size, with request volume approximately unchanged. Comparing these 2 measures before and after the prompt change directly shows whether token growth is driving higher inference cost. Now consider why the remaining options are unsuitable. C. Git commits do not measure model inference usage. D. An unrelated index's vector dimensions do not explain prompt/completion token cost. E. Evaluation dataset count is not an inference consumption metric. Remember this distinction for the exam. Separate input and output token trends when investigating GenAI cost changes. prompt growth and response growth can have different causes. Proceed to question number 118. We are moving to coherence evaluation. A Microsoft Foundry evaluation shows that assistant responses are grammatically readable, but reviewers complain that ideas are presented in a disorganized order and the connections between sentences are difficult to follow. Which built-in quality evaluator most directly measures this problem? Available choices. Choice A, coherence. Choice B, groundedness. Choice C, relevance. Choice D, fluency. The required response is option A, coherence. The key reason is coherence measures the logical and orderly presentation of ideas and whether connections between sentences and paragraphs make the response easy to follow. The incorrect choices fail for the following reasons. B. Groundedness measures support from supplied context. C. Relevance measures whether the response addresses the query. D. Fluency focuses on language quality and readability rather than primarily on logical organization. A useful examination rule is this. Coherence equals logical flow and organization. Fluency equals language quality. Groundedness equals source support. Relevance equals pertinence to the query. Now consider question number 119. Background. A multilingual legal search (RAG) application is being rebuilt with Azure-hosted embedding models. Current environment. The team is comparing text, embedding 3, small, and text, embedding 3, large. Business requirements. Retrieval quality across multiple languages is the top priority. The organization can accept higher vector storage and compute cost when justified by better retrieval quality. Technical requirements. Use the stronger general-purpose embedding option and validate it on representative retrieval queries before production. Which embedding model should the team test as its primary candidate? The options are Choice A, text, embedding 3, large. Choice B, text, embedding 3, small. Choice C, whisper. Choice D, GPT 4.1, mini chat completions. The correct answer is option A, text, embedding 3, large. The requirement is satisfied because text, embedding 3, large is the more capable third-generation Azure-hosted embedding option and has stronger published multilingual retrieval benchmark performance. The scenario prioritizes retrieval quality over the extra vector storage and compute cost. The remaining options are incorrect because B, text, embedding 3, small can reduce cost, but does not best match the stated quality first requirement. C, whisper is an audio transcription model, not an embedding model. D, a chat completions model is not a vector embedding replacement for this retrieval layer. Keep this examination point in mind. Choose embedding models by measured retrieval quality, language/domain needs, dimensions, storage, latency, and cost, not model size alone. Proceed to question number 120. Scenario. A specialized engineering RAG system still retrieves semantically related but domain-incorrect passages after chunking, thresholds, and retrieval configuration have been tuned. The team has representative query-positive passage pairs and challenging negative examples for the engineering domain. It wants the vector representation itself to better capture domain vocabulary and relevance. Which optimization should the team evaluate next? Review the options. Option A, fine-tune a suitable embedding model on domain-specific retrieval pairs by using a contrastive learning approach, then re-evaluate retrieval quality. Option B, increase the chat model temperature so retrieval vectors become more domain-specific. Option C, fine-tune only the response generation chat model and leave retrieval quality unmeasured. Option D, increase the generation max_tokens value for every request. The best answer is option A, fine-tune a suitable embedding model on domain-specific retrieval pairs by using a contrastive learning approach, then re-evaluate retrieval quality. The reasoning is as follows. The remaining problem is the embedding representation itself. Domain-specific query/positive/negative relationships can be used for contrastive embedding fine-tuning so relevant items move closer in vector space and confusing negatives move farther apart. B. Generation temperature does not train retrieval embeddings. C. Fine-tuning only the generator does not repair poor vector retrieval. D. Max_tokens affects generated response capacity rather than embedding quality. Exam tip. Fine-tune embeddings only after diagnosing an embedding quality problem. Validate the new representation with retrieval metrics on representative queries. Question number 121. Next, we enter the topic of hybrid retrieval. Background. Apart support, our AG application uses Azure AI Search. Current environment. Users ask conceptual questions such as, which pump is suitable for corrosive fluid? And also search exact identifiers such as PX 4107. B. Vector-only retrieval handles conceptual questions well, but occasionally misses exact part identifiers. Business requirements. The retrieval layer must preserve semantic matching while improving exact term and identifier recall. Technical requirements. Keep vector retrieval and add a supported retrieval strategy that can use keyword matches in the same search request. Which retrieval strategy should the team implement? Option A. Hybrid search that runs full text and vector queries together and merges the ranked results. Option B. Keyword-only search that removes all vector fields. Option C. Vector-only search with a higher generation temperature. Option D. Randomly alternate between keyword search and vector search for each request. In this case, select Option A, hybrid search that runs full text and vector queries together and merges the ranked results. Here is the technical justification. Hybrid search combines keyword/full text precision with vector semantic similarity in one request. Azure AI Search executes both retrieval paths and merges their results, improving exact code retrieval without sacrificing conceptual matching. The alternatives can be eliminated because B. Keyword-only search would lose vector semantic retrieval. C. Generation temperature does not change search matching. D. Random alternation prevents each request from benefiting from both retrieval methods. Hybrid search is especially valuable when our AG must handle both semantic concepts and exact terms such as product codes, names, or specialized jargon. The next item is question number 122. Review the situation. A team has a production RAG configuration and a candidate retrieval configuration with different chunking and hybrid search settings. It wants a reproducible A/B style evaluation before promoting the candidate. Select the 4 required actions and arrange them in a defensible comparison order. One item will not be used. The available items are: Entry 1. Promote the candidate before measuring it so production users can decide. Entry 2. Establish baseline retrieval and answer quality metrics for the current configuration on a representative evaluation set. Entry 3. Run the candidate configuration on the same evaluation set and collect the same metrics. Entry 4. Compare baseline and candidate relevance, groundedness, and other agreed acceptance metrics. Entry 5. Promote the candidate only if it meets the predefined improvement and regression thresholds. The completed sequences. First, establish baseline retrieval and answer quality metrics for the current configuration on a representative evaluation set. Second, run the candidate configuration on the same evaluation set and collect the same metrics. Third, compare baseline and candidate relevance, groundedness, and other agreed acceptance metrics. Fourth, promote the candidate only if it meets the predefined improvement and regression thresholds. A defensible retrieval experiment controls the evaluation data and metrics across baseline and candidate configurations. Comparing equivalent relevance and answer quality measures before promotion prevents production traffic from becoming the first validation step. The key takeaway is for our AG/AIB tests, hold the evaluation set and metrics constant, change the candidate configuration, compare, then promote by predefined criteria. Now consider question number 123. Background. Contoso trains a fraud detection model in an Azure machine learning development workspace and promotes approved models to a separate production workspace in another subscription. Current environment. Both workspaces belong to the same Microsoft intratenant. A central Azure machine learning registry is used for governed production candidates. Business requirements. The production workspace must deploy the exact approved model version without copying the training job or rebuilding the model package. Technical requirements. Preserve model lineage and use supported cross-workspace registry behavior. Which 3 actions or conditions are required for this promotion approach? Choose 3. Choose every option that satisfies the requirement. The options are: Choice A. Publish the approved model version from the development workspace to the Azure Machine Learning Registry. Choice B. Ensure the production workspace region is supported by the registry. Choice C. Deploy the model from the registry to an endpoint in the production workspace. Choice D. Copy the development workspace compute cluster into the registry before model promotion. Choice E. Re-register the model from local files in production so the registry version is not referenced. The choices that satisfy the requirement are option A. Publish the approved model version from the development workspace to the Azure Machine Learning Registry. Option B. Ensure the production workspace region is supported by the registry. And option C. Deploy the model from the registry to an endpoint in the production workspace. This is correct because Azure Machine Learning registries provide a central cross-workspace asset catalog. An approved model can be shared to the registry and deployed from that registry into another supported workspace while preserving version lineage. The other choices do not satisfy the requirement because D. Compute targets remain workspace resources and are not promoted through a registry. E. Re-registering local files in production bypasses the governed registry version and weakens lineage. Remember this distinction for the exam. Use registries to promote version models, components, environments, and data across workspaces. Compute remains workspace local. You have completed Set 3 of the AI-300 Microsoft Certified Machine Learning Operations Engineer Associate Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Koushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.